we have a portion of CaCO3 over there in that exchange, meaning that portion of calcium carbonate, it is the one that is going to react completely. All right. So once it's react completely, that means this one is going to be our limiting reagent in that case. And then having said that, for our excess, for this guy, the excess, it was left in the beaker. Meaning, okay, let me just make a simple scenario, because some of you were saying you don't understand what happened. Fine. And then we have one beaker over there. Let's say this one is CH3, COOH, adding it with CaCO3. So when we mix them together, mixing these guys together, we are going to get what? We're going to get a solution over here. We get our product, maybe what was our salt? What was our salt? What was our salt? Let me just say a salt in this case. But the thing is, here on this one, it was left in the beaker. This is our excess, and it was our excess. Meaning, if I were to make numerical example, I can say this one was having 4 moles, okay? And then this one was having maybe 2 moles. So when they react, the calcium carbonate is going to donate its 2 moles over there. And then this one, our acetic acid, will also donate 2 moles. So when they donate those 2 moles, they're going to react with each other and use each other up. And then the thing is, this guy will be left with 0 moles because it has reacted with all of its 2 moles. And then because this guy, the excess, he only gave away 2 moles and then the reaction was complete. It means that he is still left with 2 moles. Okay, that's why it is an excess. It still has an amount or a certain amount of moles in that case. Now, the second statement said acetic acid that remain unreacted is neutralized by 25 cubic centimeter of sodium hydroxide with concentration of that one. Then they gave us the equation. Now, what they did, and get the acetic acid, it was left unreacted. 2 moles were left unreacted. They then took, those 2 moles over there. When they took them, they said, okay, we still have CH3, COOH in our beaker, and now it is 2 moles that are left. We're taking those 2 moles. We're still going to react them with another NaOH of certain mole. We don't know the number of moles here. Let me just say unknown in this case, because we can calculate these ones. We can calculate these ones. Now, our product side, let's just say we have a salt. I'm not going to talk about the water. Let me just say we have a salt over there. Now, the very important thing that you must understand, or that you must always bear in mind, the number of moles that you have in the first beaker, those are the initial number of moles. Initial. Ish, the spelling. Damn, what a nice English. Those are the initial number of moles. Okay. Then now, the number of moles that we have in the second reaction, those are the number of moles that were in excess. Why? Because this number of moles were left, okay? In meaning the solution was excess. It was excess because 2 moles were left. And then we took those 2 moles and reacted them with something else. Meaning those number of moles that we took, the 2, it is actually our excess number of moles. Now from there, what we need, what we're going to need is actually the number of moles that have reacted. Okay, and what I want to tell you guys, just keep this formula now. The formula that you are going to use in questions like this, whereby you have double reactions, an excess reacting in another reaction, you're going to use this formula. The initial Spelling. The initial number of moles is equal to the number of moles that have reacted plus the number of moles that are in excess over there. But mainly, the way you use it, you are going to use it like this. This is the general. Let me say this is the general. General. The way you use it, you have the number of moles that have reacted because you always have to find the number of moles. In most cases, not always, in most scenarios, they want the number of moles that have reacted. I will show you why. And then the number of moles that reacted is equal to the number of moles that were in the initial solution minus the excess. Okay, say, now I don't understand. Okay, fine. Look at this. In our initial solution, before the reaction took place, the number of moles that we had, it was 4. We had 4 number of moles. That is the initial number of moles. It's 4. But again, in our excess solution, we got or we found out that only 2 was in the excess solution. That means if I subtract that 2, what am I going to get? I'm going to get a final answer of what? 2 moles. Say, what do you mean? I mean, look at my reaction when I was explaining the reaction there. I said the excess will contribute, the 2 will contribute that 2 over there into the reaction so that that 2 react with calcium carbonate and that give us our product over there. Meaning, you always have to find this guy by using this formula in most cases, because in some cases they will want you to calculate the initial number of moles and so on and so on. Now let's get to the calculation itself and see how we do them. You always, okay, I will try to write steps that you can take. Let me erase over there. Gone, then gone, and gone, and gone, and gone, and gone, gone, and gone. So it's, yeah, this is much perfect now. Now let's start. Let's get to work. Getting ready. Now, for this one, you always start in this last reaction. You always start at the last reaction. But also, if you are very strategic, you can still start in this reaction. Anyway, it's fine. But okay, it's fine. Because I'll be writing step by step, I will actually start at the first reaction. Okay. And then now, because the statement was saying Ori, an excess amount of standard dilute acetic acid solution of concentration 0.5, what, and so on and so on. And then acetic acid, that acetic acid, CH3COOH, it had a volume and also a concentration, okay? Meaning the concentration was 0.5. And then the volume was what? The volume was 250 cubic centimeter. Can someone convert me the volume? Can someone convert me 250 into cubic decimeters? 0.5. What is 250 divided by 1000?
0.25.
That's 0.25 over there. The first thing that you are going to calculate, you are going to calculate the number of moles. And then it means that you're going to say C is equal to N over V over there. And then you have 0.5 is equal to N over the volume of 0.25. And then what is the number of moles? Zero point five
0, 0.125.
0.125 moles. So these ones, this is the initial. Those are the initial number of moles. Why? Because we are using the information displayed over there. They said an excess amount of standard dilute acetic acid solution of concentration 0.5 and volume 250 is allowed to react. Meaning, we then took this thing, that acetic acid of that information, and reacted with calcium carbonate. And then that's why I'm saying those are the initial number of moles, because before the reaction started, we had a volume of 0.5 and a concentration of 0.5, and then it was then reacted with calcium carbonate. I hope I'm clear over there. Now, the second thing that you must do, come to the second equation and check the information that you have. The information that you have, they said acetic acid that remained unreacted is neutralized by 25 cubic centimeter of sodium hydroxide with a concentration of 0.968 over the mole per cubic centimeters. Okay, you have the information of your base. You have the information of your base, which is NaOH over there, which is C is equal to 0.968, I think. And then also the volume of, can you convert 25 into cubic centimeters? Because it was cubic decimeters, not cubic centimeters.
0.0225.
0.025. All right.
Yes, sir.
Okay, thank you. So meaning you can still want to find the number of moles. Okay, can still want to find the number of moles. So I'm going to say C is equal to N over the volume. What is your concentration? 0.968. What is your number of moles? You don't know. What is your volume? 0.025. And then you find the number of moles. What is the number of moles?
0.0242.
0.024246.
242.
All right, moles over
Sir,
there. Yes,
242.
242. Okay, sorry about that. 242. That's 242 moles right there. Now, this is for the base. And that base, which is an AOH, it has reacted with acetic acid in the second reaction. Now, what you need to do, you must find the number of moles of your acetic acid that reacted with the base. And the way you do it, to find the number of moles of acetic acid that reacted with sodium hydroxide, you must use the mole ratio. H3 COOH2 NaOH. Here we are finding the number of moles of acetic acid that reacted with sodium hydroxide over there. And then, what is the stoichiometric ratio? It's 1:1 because they said the equation is balanced. We are fine. 1. And then what is the number of moles of acetic acid? I don't know. NCH3 COOH. And then what is the number of moles this side? 0.0242. And then the number of moles of acetic acid, CH3COOH, is equal to 0.0242 moles over there. So now, the thing that happens is, these are the number of moles in excess. These are the number of moles that are in excess. Okay, say I've lost you for a minute. Fine. We had this information But don't forget that I said this guy, this is the excess solution. So whatever information of this guy that you will find, it is for excess. Okay. So that excess was reacted with the base. The excess was reacted with the base. That is why we used the stoichiometric ratio between the base and our excess solution over there. I don't know if I make sense in that case, but fine. Now in this case, so now we have the initial. Then we also have what? We also have the excess. What do we need? We need the reacted number of moles. That's what we need. So to find the reacted number of moles, we say number of moles that are reacted is equal to number of moles in initial stage, minus the number of moles that are basically in excess. So which is going to be 0.125, that's 0.125 minus 0.0242 in that manner. What do you get?
0,1008 moles, sir.
0.1008 moles in that manner. Now, having found the number of moles, don't forget that this is the number of moles of CH3COOH. Guys, these are the number of moles that have reacted. They reacted with what? With CaCO3, calcium carbonate. Here. They reacted with this guy. Those number of moles, they reacted with that guy. So if they reacted with that guy, it means that if I use the stoichiometric ratio between this one and that one, I'll find the number of moles of calcium carbonate that have reacted. What I'm saying is, if I take this one to this side and say what? The number of moles of CH3COOH to the number of moles of CaCO3. The number of moles of this one that are reacted with that one. The ratio is going to be, what is the stoichiometric ratio? 2:1. That's 2:1 over there. Now, what is the number of moles of acetic acid? That's 0.00, or not 0.1008 is 2, and then is to the number of moles of calcium carbonate, of which it's unknown, CaCO3 over there. And then when I cross multiply, I'm going to get 2 and CaCO3 is 2, 0, not is 2, is equal to 0.1008 over there. And then when I divide both sides by 2, NCaCO3, what is the number of moles over there?
0,0504 moles, sir.
0.0504.
504.
Moles over there.
Yes, sir.
So it means that now I'm going to simply calculate the what? The mass, because I have the number of moles. I have the number of moles of calcium carbonate that have reacted. And don't forget that because that guy is a limiting it's actually okay, I mean in that eggshell, only the portion of calcium carbonate reacted. So it means that this number of moles are for the pure sample, which is for the CaCO3 over there. That's why I'm going to find the mass, and that mass, it is the pure mass of our compound or our sample. So that means I have N is equal to M over M over there. So what I'm simply going to do, I'm going to input my values. I have 0.0504 is equal to, what is my mass? I don't know. What is the molar mass? Molar mass of calcium carbonate, it's 100. I know that one. And then what is the value of our mass when you cross multiply? M is equal to 5
5,0.04.
0.04 gram in that manner. Now, the thing that we wanted, it was percentage purity, because don't forget that this is the pure, okay? That's the pure mass. But in our equation, they gave us the mass of the entire sample, which is actually the impure sample, okay, which is 56 impure sample, which means now, because I have the pure, I can say percentage purity is actually equal to pure mass divided by impure sample multiplied by 100, and that's going to be 5.04 divided by 56 multiplied by 100. What answer do we get?
9%.
That's going to be a 9% over there. So that's how you do it. That's how you do it. So the very important